All right, for our next half of Unit 2, we're going to focus on making sure that we know how to simplify square roots. So this is really just a review lesson. It's stuff that you've done before. I would love for you to have these explanations and examples in your notes so that you can reference them while we simplify square roots for the next several weeks, all right? We're gonna be doing a lot here today that is basically the entirety, maybe not the entirety, but pretty close to at least 2 or 3 sections of what you did in Algebra 1. We're gonna do kind of in one fell swoop here. And so our goal is to simplify expressions that involve square roots, specifically square roots. There's some key vocabulary terms here, and we'll kind of talk about some of these as we try to write our expressions in their simplest radical form. The focus today is explicitly with numbers instead of numbers and variables, and so this should help us. Real quick, squaring a number is simply multiplying it by itself. So, 1 squared is 1, 2 squared is 4, 3 squared is 9. You should know all of your perfect squares, even past your times tables, all right? We know that your times tables go up to 144 in your elementary arithmetic, but also you should know that 13 squared is 169, that 14 squared is 196, that 15 squared is 225, and you might even want to go all the way to 20 and have all of those perfect squares as well. So go ahead and fill out that table right there with all of these perfect squares, because we're going to be referencing undoing the square operation by taking square roots. So if I'm talking about the square root of 4, we should know that that's 2. And the principal square root of 9 is 3. And the square root of 64 is 8. The square root of 169 is 13. That's really the goal there. And so this number that's under that square root sign, so that square root sign is really a radical sign, is really what that's referring to. This is called the radicand. There's an index here. This is blank because it implies the second root, the square root, but you could have a cube root. You could have 4th roots, 5th roots, etc. We typically deal with square roots. And the square root of 27 is not going to be a rational number. But we do know that the square root of 27 can be broken down as square root of 9 and the square root of 3. And we know what the square root of 9 is. We know that the square root of 9 is 3. And so we're going to learn and we're going to explore how to write in simplest radical form. Again, this is work that you did in your Algebra 1 days, and the whole punchline here is we want to be able to write our expressions in their simplest radical form. And so simplest radical form has basically 3 rules. 1, no perfect square factors in the radicand. All right, so that's underneath the square root sign. No fractions in the radicand, so you can't have a fraction inside of the square root. You can, but then it's not simplified. You have to then simplify it. And there cannot be any radicals in the denominator of a fraction, all right? So anything in the denominator, we will either have to rationalize that, or if we can actually take its square root, then we will take its square root. So these are kind of the 3 big rules of simplifying square roots. There are these 2 properties, the product property and the quotient property for radicals, and this works with all radicals. If the index is some other number than 2, all right, so if you have the nth root of a times the nth root of b, that's the same as the nth root of a times b. I have it written in both ways because sometimes we're going to try to multiply them and put them together. Sometimes they're going to be together and we're going to want to take them apart. So it works forwards and backwards. And so that's why I have that written. If you don't want to write what's after that equal sign, that's fine as well. And you can just have this as a property. That's totally fine as it's written here. All right, but these are our 3 rules, and so we're going to reference those rules as we work through these examples. And now these examples, again, the goal here is for you to be able to do the simplifying of square roots as much as is humanly possible. And so the way that we approach this when we're first learning it in Algebra 1 is we try to break down these numbers into perfect squares, all right? 192 is not a perfect square. If I take the square root of 192, I'm going to get something just shy of 14, all right? Some irrational number that's smaller than 14. And so really our goal here is we want to see what is the greatest perfect square factor of 192. Now there's a lot of different tweaks that you can do. You can say, well, I'm pretty sure I know that's an even number, so I can do like factor trees like we did in whatever grade that was, where we did was 96, and then this is 2 times 48, and then this is, oh, I know that 48 is 2 times 24, and that 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. And so what they had you do in ninth grade math is they would say, all right, well, you've got all of these 2's, 1, 2, 3, 4, 5, 6 2's, 3, 4, 5, 6 2's, and then it's left over 3, right? And if you could pair them up, then they could come outside. If you could pair them up, then they could come outside. If you could pair them up, then they could come outside. So now we have this 3 that's left inside, but on the outside we have 2 times 2 times 2, and that makes 8 squared to 3. So that is kind of the long drawn out process that you went through in Algebra 1. And my opinion of that is not that that's bad, it's just that it takes forever. And what you can do is, in the meantime, you can think of shorter ways to get that answer by finding the greatest perfect square factor, doing a little simple division. So for example, I might look at this and say, oh, I know that this is, 16 times, it's 16 times 12 is what my calculator tells me. Well, I picked 16 for a reason. I picked 16 because it's on our list of perfect squares, and I can take the square root of 16. But what we should know about 12 is that 12 can also break down more. 12 can break down as 4 and 3. And so if we can find perfect square factors, it doesn't have to be the biggest perfect square factor, then when we write these in their simplest radical form, separating them out, we'll have the square root of 16, the square root of 4, and the square root of 3, I don't know what that is, so this gives me 8 times the square root of 3. Or, if you want to be the most efficient, you can recognize that this is actually 64 times 3. That's not on our times tables though, so that might be a difficult task for you to recognize that this is 64 times 3 to get 8 times the square root of 3. Folks, regardless of how you do it, you're going to get the same answer if you're doing it correctly, right? If you have the correct pairs of numbers and the correct perfect square factors that you can break down. But what I want for you to recognize is here, 4 times the square root of 12 is equal to 8 times the square root of 3. If I type those in the calculator, and I do 4 times the square root of 12, and I do 8 times the square root of 3, and I do the square root of 192, these are all the same amount. They're all the same. Because they're all equivalent to each other. But only one of these is in simplest radical form, and that is 8 square roots of 3. All right, 8 times the square root of 3. So we want to find the greatest perfect square factor. 18 is 6 times 3. Neither one of those are perfect squares. But we know that 9 and 2 has a perfect square factor. The square root of 9 is 3. The square root of 2 we can't do. All right? You go ahead and do this one. You do letter C there. Simplify the square root of 80. Can you find the greatest perfect square factor of 80? Or do you need to do factor trees, or whatever other gimmicks or tricks you may have learned in your middle school class? All right, multiplying radicals. When we are multiplying radicals, we get to do this a couple different ways. One, if we use that product property of radicals, we can put these together and multiply 3 times 24, and then simplify the big number that we get, the square root now of 72. All right, square root of 72, that breaks down with the greatest perfect square factor of 36 times 2. We know the square root of 36 is 6. The square root of 2 we don't know, so we get 6 times the square root of 2. Like I said, though, there's maybe other ways we could do that. For example, we could break that down as the square root of 3, and then we could take 24 and do that as, well, that's going to be 3 and 8. I know that 8 can break down more. These are going to come together and give me 9. This is going to break down as 4 and 2. And so now I have the square root of 9, the square root of 4, and the square root of 2. This gives me 6 times the square root of 2. So you can do that really in whichever way that you would prefer. Some of these might seem like that one looks shorter than this one. It's really the same amount of steps, all right? This got a little bit bigger, and then I had to break it down from there. Here, we kept them separate and made them small and manageable. Here, we're going to use the commutative property of multiplication to change the order. So I get 12 times the square root of 20. I know that 20 breaks down as perfect square 4 and 5, a prime number. Oops, the square root of 4 is 2. The square root of 5 I can't do, so I get the square root of 5 times 24, or 25 times the square root of 5. Dividing radicals. If we are dividing, remember we've got these rules that say I can't have a fraction in my square root, so this is not simplified. Furthermore, I can't have a square root in the denominator of the fraction. And so by using the quotient property of radicals, I'm going to break a rule, all right, and put that instead of now I have a fraction in the square root, but I have a fraction that can be simplified. Now I have no more fractions. No radicals in a denominator, no fraction in the radicand, but I do have a perfect square factor in there. Square root of 4, square root of 2 gives us 2 square roots of 2. 48 and 75. All right, we're going to find here that if I simplify this fraction, this is 3 times 16 over 3 times 25, that this actually simplifies to be the square root of the numerator divided by the square root of the denominator, and that gives me 4/5. All right, simplifying the fraction first can be helpful. All right, and so if we simplify the fraction first, that can be useful. Other times we might not find it quite as useful, but here it seemed to work for us. Rationalizing denominators. So what happens if, like with this, I could divide and I can simplify the fraction and no more issues. Here I divided and I got a number that I can take the square root of, so that worked out nicely. But on these right here, I have a square root of 5, and I can't do anything with that. Square root of 18, I can simplify the square root of 18, but I'm still going to have a square root of 2 in there, and I have to figure out how to handle that. So here's what we're going to do. I'm going to multiply by 1. And when I multiply by 1, it gives me, the same thing, right? Multiplying by 1 sounds a little bit silly. So here's what we're going to do. Just like when you had fractions that didn't have common denominators, you would multiply them by another fraction to get an equivalent thing. And so what we're going to multiply by is the square root of 5 over the square root of 5 so that I get the square root of a perfect square. All right? On the numerator, when we multiply fractions, or denominator, it gives us this product, all right, which we can now take the square root of 25. Up on top, I can multiply them, right? It gives me that expression, that can't be simplified more, and as long as my fraction is simplified before I start rationalizing, then my fraction is done. Over here, we might find that instead of multiplying by the square root of 18 over the square root of 18, it may be beneficial to simplify the square root of 18 as the square root of 9 and the square root of 2. All right, because when we do that, we have 3 square roots of 5 over 3 square roots of 2, and you know that that's going to equal the square root of 5 over the square root of 2. All right, because the 3's will factor out as 3 over 3 is equal to 1. So now we have the square root of 5 over the square root of 2, and we're going to do the same work that we did here. We're going to multiply by 1, but represent 1 as the denominator over itself. I'm picking the denominator because that's going to give me, in the denominator, the square root of a perfect square. If I make it so that I get the square root of a perfect square, then I end up with a fraction that does not have a radical in the denominator. All right? And as long as we simplify first, we don't have to simplify later. So that may be one of those things that you decide, I don't want to simplify now, I'd rather simplify later. Great, you can multiply by square root of 18 and square root of 18. You'll still end up with the same answer. You're just going to do a lot more work. Right? And that may be just a lot more work on that exercise, but it may be less work on another exercise. All right, for this last little bit, here we have some expressions where we have fractions and radicals in the numerator fractions. We've got sums in the fractions, and I know that we tend to struggle with fractions quite a bit here in America, but we are going to do our best work to make sure that we can simplify these expressions well. We know that our square root of 48, we've already explored and explained that we can rewrite that as the square root of 16 times the square root of 3. So I have 2 plus 4 square roots of 3 over 8. Now these are not like terms, so I can't just add these together. 2 times the square root of 48 is not the same as 2 plus the square root of 48. Likewise, 2 plus the square root of 16 times the square root of 3 is not 2 times the square root of 16 times the square root of 3. And 2 plus 4 times the square root of 3 is not equal to 6 square roots of 3. So you have to understand that this does not equal 6 square roots of 3. If you want convincing evidence of that, I can type in my calculator 2 plus 4 square roots of 3, and I can type 6 square roots of 3. and these are not the same number. They are different because these are not like terms. This one has a radical, this one does not, so I can't combine those willy-nilly. But what I can do is I can recognize that this fraction can be simplified. Now there's a longer way and a shorter way, so let me kind of explain the longer way. When we add fractions, we have a common denominator and we just add the numerators, right? We put the sum of the numerators over that common denominator. Well, here we could say that this is 2 over 8 plus 4 squared is 3 over 8. All right? And if we can do that, then that means that we can simplify each separate term in here. And we can write that as, well, this is 1/4, and this is 1/2 times the square root of 3. And so this would be our simplified form. Now, some teachers don't like these to be separated. Instead, what we want to do is, if we can, what if I can just factor out a common factor from the top and write that as 2 times 1 plus 2 square roots of 3. And in the denominator, we have 2 times 4. If I recognize that by factoring out that common factor, I can simply eliminate this factor of 1, this 2 over 2, and I'm left with 1 plus 2 square roots of 3 over 4. All right? Now, one is not necessarily better than another, all right? Both of these are correct, and I can't think of a situation where I would mark this one wrong but then give you credit for that, or not give you credit for that instead, or mark this one wrong and then give you credit for this one. So that's not the point here. The point here is to say these are the same thing, and they're both simplified. The reason why this one is quote-unquote better for our purposes is because we are going to be doing the Pythagorean theorem. I've been in geometry for too long. The quadratic formula, where we're going to have x is equal to the opposite of b plus or minus some square root. All right, so we're going to have over 2a, right? So we're going to have a opposite of b plus or minus the square root of b squared minus 4ac all over 2a, and we're going to have to simplify it. And most of us are going to want to simplify it like this, but this is perfectly acceptable, all right? And most of my answers are going to look like this, whereas this is perfectly acceptable, all right? So just kind of keep that in mind. Same thing's going to happen over here. Let's see if we can break down. Well, how about I have you do this? How about I have you, you're like, no, please, no, don't make me. But take this square root of 120 and see if you can break it down. If you want to think of these as separate fractions, then you can do that. If you want to keep them together, then do that. I would love for you to give this your best shot. You try to do it, all right? All right, it's only, let's give it a shot. What's the worst that can happen? The worst that can happen is that it's wrong, all right? And I'll give you the right answer next time we're together. All right, so that's really it, folks. This, hopefully, you know this vocabulary. What is a radical? What is the radicand? What is simplest radical form? And hopefully you recall work that you did in Algebra 1 with simplifying radical expressions.